In Lesson 3.1, we will be discussing exponential functions. In Video 3.1.2, we will have a learning target for students to evaluate, graph, and analyze exponential functions. In Example 1, we were asked to graph some different types of exponential functions. It is typical for exponential functions to have two different types, growth and decay. Exponential growth functions, which we see on the right here, are strictly increasing. They increase from negative infinity to positive infinity. They're continuous from negative infinity to infinity. There's no breaks or discontinuity. As we move to the right, since y is increasing as x approaches infinity, you would say the end behavior as x approaches infinity would be infinity. And as x approaches negative infinity, your limit is going to be, or your end behavior is going to be approaching 0. Now, we don't have any extrema here. Extrema, I'm talking about maximums or minimums, because the graph increases infinitely and never actually has a low point either. So it never has an absolute maximum or an absolute minimum. So we would say no extrema or none. And asymptote, our asymptote, we have a horizontal asymptote at the x-axis because as x approaches negative infinity, our y-coordinate, this graph flattens out and our y-coordinate is approaching 0. We have no x-intercept. We never actually cross the x-axis, so there's no x-intercept. Our y-intercept, or where we cross the y-axis, is at 1. Since our function is continuous, our domain is negative infinity to infinity. And since our y-coordinate can never be less than 0, we say our range is from 0 to infinity. And we get the infinity because our function is increasing infinitely. Or our right end behavior is pointed upward. Okay, exponential decay has many of the same features, except for this time our function is decreasing. One thing I didn't note on the exponential growth function is that you only have a growth function when your base or your b value is greater than 1. You have a decay function when your base or b value is between 0 and 1. You have a domain that's from negative infinity to infinity because your function is continuous. You have a range still from 0 to infinity because the function is decreasing infinitely and is going to approach 0 but never actually equal 0. Our y-intercept is still at 1. We do not have an x-intercept for any exponential function, any basic growth or decay function at least. And for an extrema, we don't have an absolute maximum or minimum on this graph, so therefore we would say no extrema. Our asymptote, again, is going to be the horizontal asymptote at the x-axis because the right end behavior this time, the right end is approaching 0 as we approach infinity. That end behavior is noted here. The left end is moving towards infinity, so as x approaches negative infinity, y is approaching infinity, and as x approaches infinity, positive infinity, y is approaching 0. And for continuity, you have, it's a continuous function, so therefore it's continuous on the interval from negative infinity to infinity. In example 2, we're going to graph transformations of exponential functions. We're going to use the knowledge we have from Chapter 1 about transforming functions, so vertically expanding them, horizontally expanding them, translating left and right. But this time we're just going to be looking at strictly transforming exponential functions. So in part A, we have the function f of x equals 1/2 raised to the x. That's our parent function or our original function, and we need to use that to describe the transformation that results in g of x, which is 1/2 raised to the x plus 1. Then sketch the graph of the function. Okay, if you remember some things with transformations, anytime we add something to x, since x is our horizontal axis, right? The x-axis runs horizontally on our graph. anytime we add something to x or subtract something from x, that shifts our graph horizontally. All horizontal shifts, or all, I'll say all horizontal transformations or translations. Translation is a slide. Those occur opposite of sign. So when I see a +1 to this function, when I'm adding 1 to x, it actually takes the original function and slides it 1 unit to the left. The reason why I say it's opposite of sign is because you would think adding 1 to x would actually shift the graph to the right one, but it actually has the opposite effect, and we're going to say translates to the left 1 unit. And we'll go ahead and sketch the parent function along with this function on the next slide. If you graph in y1 your parent function, which is f of x, and you would have 1/2 in parentheses raised to the x power. In y2, I would want you to type in 1/2 raised to the x plus 1. And what happens is you're going to see all the values, all the ordered pairs, shift to the right one, to the left one rather. And here's the dotted functions, our parent function. If we look at points, some specific points on this parent function, you can notice that those points on the translated function have been translated 1 unit to the left. Everything has been shifted 1 unit to the left. If I had a point right here, it is now moved 1 unit to the left. So you can take any point on the original function and shift it 1 unit to the left. Plot both of those graphs on your x and y coordinate plane. And you have the graph of your function. And on the last slide, we described that it was a translation 1 unit to the left. Okay, in example 2 part B, we're asked to use the original function f of x equals 1/2 raised to the x to describe the transformation that results in h of x, which is 1 over 2 raised to the negative x. And then we're going to sketch the graph of the function. If you remember from chapter 1, when we change the sign on our independent variable, or x, that results in a reflection over the y-axis. We're changing the sign on x. So if you think about a coordinate plane, if x was +1 before, now it's -1. And so therefore a point that would be in the first quadrant now has an x-coordinate in the second quadrant at -1. And so you're taking any point in the first quadrant and you'd be reflecting over the y-axis, which would land in the second quadrant. Okay, so basically we're saying that if x starts out positive, now we're changing the sign. Even if x started out negative, let's say somewhere over here, if we started at -3, reflect that across the y-axis or make it positive. +3 is now over here. So you can see that by changing the sign on your x coordinates, that reflects those points over the y-axis. So I know that f of x is a parent function. H of x is going to be a reflection of f of x over the y-axis. On the next slide, we will go ahead and graph both f of x and h of x on the same coordinate plane. Here we have the graph of f of x and h of x. In your graphing calculator, you could type in the original function, 1/2 raised to the x power, and in y2, you could graph 1/2 raised to the opposite of x, or negative x. Make sure you use the negative sign, not the subtraction sign in front of x, otherwise you'll get a syntax error. And any point that is on the y-axis, since we're reflecting f of x over the y-axis, if the point is on the axis of reflection or axis or line of, how do I want to say this? If a point is on the reflection line, I should say, when you reflect that point, it lands on the same line. So this point is going to stay put for both functions. Now let's think about this point right here. On the original function, if I reflect that point over the y-axis, since it's 2 units away from the y-axis, it'll be 2 units away from the y-axis on the other side. So there gives me my ordered pair on the other side of the y-axis. If you think about another ordered pair here, let's say this point right here is a roughly 3.3 units away from the y-axis, then this point on h of x is also going to be approximately 3 units away from the y-axis. So you can see from f of x and h of x that one graph has been reflected over the y-axis to obtain the other function. So we have taken f of x, our original function f of x right here is in y1. If we reflect that graph over the y-axis, we obtain the graph of h of x. In example 2, part C, we're asked to use the graph of the same parent function we've used in part A and part B to describe the transformation that results in the function j of x, which is negative 2 times 1/2 to the x. If you remember from chapter 1, anytime we multiply by a negative, anytime we multiply by a number in front of our function, that vertically expands our graph as long as the number I'm multiplying by is greater than 1. Okay, so really we're multiplying by 2 here. This negative in front of the 2 actually reflects the graph over the x-axis. Anytime you change the sign on the outside of the function, in the last example we changed the value of x. This time we're changing the value of the entire function, changing the sign out in front. That reflects over the x-axis. So here what we have is j of x is a reflection over the x-axis because of that sign change out in front. We're changing it from a positive to a negative. And then when we multiply by 2, that is called a vertical expansion by a factor of 2. I'll say by a factor of 2. Now, what we want to do is sketch the graph of both of these functions to confirm that j of x is a reflection over the x-axis and a vertical expansion by a factor of 2 compared to the original function f of x. In example 2, guided practice, we are going to use the graph of f of x equals 3 to the x to describe the transformation that results in p of x equals 3 raised to the x minus 1. Then we're going to sketch the graph of the function. I would like you to go ahead and graph the original function f of x, which the graph is shown here. And then I want you to also graph p of x and describe the transformation of that function from f of x to p of x and sketch p of x on the same axes as f of x. Having graphed p of x and described the translation from the previous slide, I would like you to choose answers A, B, or C, or D as your answer for the problem. Reference what you have from the previous slide, and then choose the correct response A, B, C, or D. And then submit your answer.